And guys, let me make sure I explain this as well, because this is just a simple drawing of a Bode network and how it works and interacts with the AGC. First thing you need to know is not all Bode networks are created equal, not all AGCs are created equal, not all backoffs are the same. Each manufacturer has a different requirement for their AGC or ADU design, and you need to follow the manufacturer's recommendation for balancing those modules. So don't walk away with what I'm telling you here and say that's the way we balance all of our modules, because each manufacturer can be slightly different, as each AGC is slightly different in design. Because the Bode network itself is really just a interstage variable attenuator, and it typically has some tilt built into that network, either on the Bode or very close to the Bode, because when we make changes when we make corrections to the output of the amplifier for changes in temperature, that's typically, we'll use a 5 to 42 system up to 1 gig, that's typically making changes from 54 megahertz up to 1000 megahertz, okay? So there's much more attenuation at 1 gig than there is at 54 megahertz. So we want to make sure when we correct for changes over temperature that we compensate, if we compensate 3 dB at 1 gig because of a 70-degree temperature change, we only need to correct for approximately 1 dB at 54 megahertz. So there is a tilt or a slope built into that correction network when we correct for changes over coax over temperature, okay? But as I mentioned, the Bode network itself has the ability to add or subtract attenuation. And the way it does that is if you follow the flow from the input to the output hybrid, you'll see your signal coming into the input of the amp. The signal flows through the Bode, and then it goes on to the output gain block, which Deanna mentioned earlier. That would be the power doubler in this case. And then at the output of the amplifier, we take a sample feed to feed to the AGC, because we want to make all the corrections to the output of the amplifier in real RF levels toward the output. Now, some manufacturers will have a conditioning pad or a control pad, and that pad is just to make sure that you have the correct levels into the AGC that will optimize the function of the AGC to its full potential. So, typically, with some manufacturers, there'll be a subtraction formula there. With other manufacturers, they'll give you a set value within a certain range of drive level. Again, follow the manufacturer's recommendation for that pad if it does have a pad location there, okay? So basically, the signal then goes into the AGC, and as it goes into the AGC, that drives a DC control line. And if you notice the red dotted line going back up to the Bode, that is a control line that supplies a DC current and voltage to the Bode network, okay? So the Bode is an intelligent network, so as that signal starts to, would you say it drops by 2 dB, typically the levels going into the AGC would drop by 2 dB, but the Bode network is intelligent enough to say, hey, I'm not satisfied with my DC voltage now. I need more DC voltage, so therefore I need to decrease my attenuation and increase my RF drive level into the AGC. So the Bode in that case would automatically take out 2 dB of attenuation so that it satisfies the voltage comparator network on that voltage, DC voltage control line. So it's intelligent enough to add attenuation and take away attenuation. There is a limit to the range that we can control an AGC and a Bode. And in this case, in this example, it's typically about 5 dB up and 5 dB down, meaning that sustain a 5 dB loss in signal are a 5 dB increase in signal. And if you run the loss performance of coaxial cable and maximum spacing between runs, what you'll see is 5 dB is typically more than enough all the way up to 1.2 gigs. So if you remember back to the older days when we had 400 and 450 megahertz systems, for those of you that have been around that long, we did not need an AGC at every amplifier. We could go every other amplifier, which was kind of the standard design back in those days. But when we go to 750 and above, we typically like to see an AGC in every trunk station, and at least 50% of the distribution are lining. And even a lot of the MSOs now have switched over to AGC in every module that they purchase, which I think is a very wise decision. So the AGC just helps hold that output level, like I said, within typically about a 10 dB range. That is when it's set up correctly, okay? That means you have the correct pad installed, or you followed the manufacturer recommendation for the setup of this AGC. So you can set these up incorrectly. You can put the incorrect drive level pad in, not perform the back off of the Bode network or the manual back off, which means you will not have any reserve gain when you need it when it gets hot in the summer months. So again, follow the manufacturer step by step for setting up these amplifiers and AGCs. I'm just trying to cover a little bit of the overview of how it works. So let's get into a little bit more detail with some of the medium advanced AGCs. Okay. This is basically an AGC that has a loss of pilot feature built into it or associated with the AGC. So if you look at this drawing closely, you'll see that there's the signal coming from the directional coupler was the same directional coupler that we had on the previous page. The drop-in pad is the same conditioning pad that we covered that you would see your manufacturer. In the case of this AGC, we're typically trying to get 8 dBmV into this AGC at 711, 609, 499, whatever your pilot frequency is. So 8 dB is the correct drive level into this AGC, and from there it goes straight into a variable attenuator, and that basically is a 9 dB adjustment attenuator that when you're setting the gain of the AGC, that's the potentiometer that you're turning. So the biggest point I want to make on this slide is some of these AGCs, not all of them, have a loss of pilot feature. So if we go down to where the arrows on the right-hand side are, that is basically a switch that will keep the AGC in the AGC operating mode. Okay, that is a voltage control switch. When the voltage of that switch gets out of its operating range, it will automatically switch to the overhead thermal position instead of driving the amplifier all the way to max gain. So when that level changes on the input, if you remember, we had 8 dB into the AGC. When that level changes approximately 8 to 10 dB, there will not be enough voltage to drive that voltage control switch. So the AGC would automatically switch out and kick into the overhead thermal position. Now guys, not all AGCs have this loss of pilot feature, and not all AGCs have the same design in the loss of pilot feature. This is just an easy one to give an example of because it's very visual. And it shows you how that switch works. If you guys remember the old A/B switches we had years ago, you can think of that voltage control switch just like an A/B switch. It's currently in the A position shown in the drawing, and when the voltage goes beyond its rated, it would switch over to the B side, which would become the overhead thermal. But again, those are things you need to check with your manufacturer with, because not all AGCs have a loss of pilot features, and some of them have a different loss of pilot function, okay, that doesn't trigger at 8 to 10 dB of less signal loss.
Oh, hey everybody, Mike Odell from Penn, Ohio SETE here. Thanks for stopping by and watching today's episode. If you like today's content, don't forget to like and subscribe. And if you have suggestions for content that you'd like to see, leave them in the comments below.